In this video, we're going to be breaking down the E2 elimination mechanism. E2 stands for elimination bimolecular. Elimination means that we are going to essentially remove a group from our substrate. Bimolecular means that we need two reactants to get this reaction started. If you compare it to SN1 and E1, those are unimolecular, which means that they just happen on their own just from the substrate. Whereas E2 is similar to SN2 in that they both need our nucleophile or base and the substrate in order to proceed. E2 is a one-step reaction where a base removes a proton, and at the same time our leaving group is going to leave, and we're going to form our double bond in that one single concerted step. So let's look at just the general mechanism. For an E2 reaction, we're going to have our strong base, and we're going to have at least a primary alkyl halide, and it needs to be primary because we're going to end up forming a double bond. For elimination, E2 and E1, we're going to end up forming a double bond. So the only way that's possible is if we have that carbon-carbon single bond at first. What's going to happen here is in one step, our base is going to attack one of our beta hydrogens. Carbon that has the leaving group is considered the alpha carbon. Any carbon next to it is considered a beta carbon, and the hydrogens attached to it are going to be called beta hydrogens. Our base is going to attack one of the beta hydrogens, and the two electrons that form that carbon-hydrogen bond are going to move to form that double bond. And all while this is happening, our leaving group is going to have enough energy to leave on its own. And this is all going to happen simultaneously in one step. If you want to show a transition state for this, you would want to show the base with a partial bond on the hydrogen, which is going to have a partial bond to the carbon, which has a solid sigma bond to another carbon, but it's going to have a partial pi bond to the carbon, who's going to have a partial pi bond to the leaving group. Our base, which is a strong base, it's negative, it's going to become partial positive. It's getting closer to neutral, but while we're in this transition state, it's not completely neutral yet, so it's partially positive. The leaving group is close to becoming an anion, but since we're kind of taking a snapshot in the middle of this simultaneous reaction, our leaving group is going to have this partial negative charge as well. This won't be an intermediate because it's way too unstable. It's just a snapshot in the middle of this spontaneous reaction or its transition state. Let's look at some key features of E2 reactions. The first is that we need a strong base. This is going to be typically an anion that wants one more proton to become stable. We can think of hydroxide groups, tert butoxide. It'll be helpful for elimination if we have some sort of steric hindrance. So that can either be in our base, our nucleophile, or in our substrate. For a strong base that is very sterically hindered, you're going to see tert butoxide a lot. And that's because we're going to have three large groups attached to our base, which is going to cause a lot of steric hindrance. And E2 is going to compete with SN2. So if there's no steric hindrance, our strong base, which most of the time will also be a strong nucleophile, will want to go SN2 because it can just squeeze in between. But if we have a very substituted base or a very substituted substrate, it's going to be a lot more difficult for there to be any squeezing through for a backside attack. So it'll be easier to just grab a proton and that's it. We're going to need a strong base regardless. The second key feature is that there's no carbocation intermediate. So this is different to E1 in that there's no rearrangements that are happening here. The third feature is that it uses anti-periplanar geometry. This means that the beta hydrogen and the leaving group must be in the same plane but on opposite sides. What does this mean? If we have a chiral carbon and we have wedges and dashes, if our leaving group is on a wedge, this beta hydrogen, not only does it need to be on the opposite side, so we're not going to see it down here, we're going to see it on the complete opposite side, but it's also going to be dashed. So this is going to be the beta hydrogen that gets removed. If there's no chiral carbons and we just see it as carbon-carbon and the leaving group, our hydrogen is still going to be the one that's furthest away, the ones that's going to be anti-coplanar. The fourth key feature is the stereospecificity. If there's only one anti-periplanar beta hydrogen, then the product geometry is fixed. So that means that it's either only going to be cis or trans or E to Z. If there's multiple beta hydrogens to choose from, our product geometry has the possibility to produce cis or trans or E or Z. The last key feature is the Zaitsev versus the Hofmann products. Zaitsev products are the more substituted alkene. That means that the two carbons that are involved in our double bond have more substituted alkyl groups. This is usually favored. But if we have a bulky base, going back to our first feature, if we have a bulky base, our Hofmann product, or our less substituted carbon, is going to be favored. And again, it has to do with steric hindrance. It's because it'll be more difficult for the bulky base to go into a place that has more substitutions, so it'll be much easier, it'll take less energy for that base to just grab one of the hydrogens off the end. Let's look at this first reaction. So we have hydroxide, which is a strong nucleophile, but also a strong base, and it's attaching this primary halide. Yes, you can argue that it could go SN2, but it very well might go E2. So we're going to look at, if it were to go E2, what would that look like? Well, we have 3 beta hydrogens to choose from. I want you to try to think of which one our hydroxide would have to attack. For an E2 reaction, remember, it's going to be the furthest, or the anti-coplanar hydrogen. So that's going to be on the opposite side. So we're going to attack this hydrogen here. And the 2 electrons from that hydrogen-carbon bond are going to form that double bond. And those 2 electrons that form the carbon-bromine bond are both going to go to the bromine, and it's going to leave. If we were to draw this transition state, we would have the OH with a partial bond to the hydrogen, partial negative here because it's going to be a full anion that's attacking. So remember, we're taking a snapshot for the transition state. As it's getting closer to neutral, it's going to have a partial negative charge. It's not going to be full negative. It's not going to be neutral. It's going to be partially negative. The hydrogen to carbon bond is partially broken. We have a full sigma bond here, and we have a partial pi bond for our double bond. And then we're going to have a partial bond with our carbon and bromine. And again, bromine was neutral. Now it's getting closer to becoming an anion in our snapshot. So this is also partial negative. This is our transition state. If we look at our product, we're going to end up with water, our H2O. That's our hydroxide after it attacks our hydrogen. We're going to end up with Br minus. And then we're going to have our organic product being CH2, CH2 with a double bond. In order to regenerate our hydroxide to keep this reaction going, there's a chance that our bromine is going to attach to one of those hydrogens and take it with it to make HBr, and then this H2O, after we get one of those hydrogens taken off, becomes the OH again, and it's ready to do the reaction again. Let's look at this reaction, where we have our alkyl halide reacting with sodium ethoxide. Our sodium and our ethoxide are going to break off into their respective ions. We can just rewrite our ethoxide as O- with CH2, CH3 with our ethyl group. We know, since it's an E2 reaction, it's going to attack one of the beta hydrogens that's opposite side of the bromine. Now we have 2 beta hydrogens. Which one is it going to be? Well, we have to look at how sterically hindered our substrate and our base are. Our base is only mono-substitute. So our base is not that large. It's almost a straight chain. And our alkyl halide is also not very sterically hindered. We don't have a lot of groups blocking these hydrogens. So that means we're going to have the Zaitsev product being the major product. Again, if we had more steric hindrance, we would see the Hofmann product as the major product. But here, we don't have any steric hindrance, so we're going to attack the carbon that's more substituted. This carbon here has two other carbons that it's attached to, whereas this carbon is only attached to one. The one carbon has two other carbon attachments. That's the one we're going to attack. And then we'll see our final product being CH3, CH with our double bond at another CH with another CH3. And then we're going to see the ethoxide getting an alcohol becoming ethanol. And again, if we want this reaction to continue, we can have the Br minus product come and take that hydrogen to form HBr, and then we get our ethoxide ready to do this reaction again. But what would it look like if we had the Hofmann product? How would we know if we're going to do the Hofmann product? Let's take the same molecule, but this time let's react it with tert butoxide, which is going to be our O minus with a tert butyl group. That's going to have 3 methyl groups attached to that central carbon. Now these methyl groups are very large in space compared to only having our ethyl group and that's it. Here we have 3 methyl groups. They're taking up a lot more space. It's going to be a lot harder for our base to maneuver and get into here. It's much easier for it to just grab this hydrogen here on the end. And that's exactly what it's going to do. We're going to end up with our organic product being the same thing, except we're going to get the Hofmann product, or the less substituted. Our double bond is going to move between the terminal carbon and then that same carbon that had the leaving group. And then again, our other product is going to be our tert butanol, which is our HO, with our CH3s, and we're going to have 3 of them. We might see the same thing where the bromine comes in, takes the hydrogen, and then we have our tert butoxide ready to go for another E2 reaction. If this video has helped you, please consider liking and subscribing. If you want to see how E2 compares to SN2 or E1, or if you want to see how SN1, SN2, E2, and E1 all compare with each other and how to figure out which one to choose, all of those videos will be linked in the description. Thank you for watching.